Heat Transfer Through Double-Paned Windows by Justin Moody. A long time ago, windows used to be made out of a single pane of glass, although this became a problem because you'd lose a lot of heat from the building through the window. And so what they've done now is they've designed double-pane windows, which has this air cushioning between the windows that really decreases the heat transfer. Although, because double-pane windows are designed to only allow heat in, or only allow light in and prevent heat transfer, it's important that you have the right amount of spacing. The reason being is if you have too much spacing, you get a circular flow of free convection, which creates a large amount of, well, relatively large amount of heat transfer. Whereas if you have too small of spacing, you get a significant amount of conductive heat transfer. The best way to test this idea is to build an experiment where you can change the thickness of the spacing between the panes of glass. And so I put together an experimental setup. These are my initial drawings of it, how it'll be done, to test the heat transfer between panes of glass with different thicknesses, and to see if we can get thinner and thinner, getting smaller and smaller heat transfer until we hit that sweet spot where it's minimized, and then you'd start getting larger and larger heat transfer again, because you'd no longer have a significant amount of free convection, but you'd have a much larger amount of conductive heat transfer. On this slide, I just wanted to show a little bit about the experimental setup. I put a lot of effort into setting all the experiment up. As you can see on the top right, I have the diagram of how the experiment will be set up. It uses two tubes to bring heat in across the first pane and then back out to get this forced convection along that surface. And then I would have a spacing that I can change, and then I guess a control surface where the heat transfer would be going that has the same cross section. And so I built this setup, and I also used 7 temperature sensors to make sure I would know what's happening all the way across. And it also gave me a good average when I didn't run the experiment, so that I could see what the ambient air was at. So on this slide, I put most of the raw data that I collected on my experiment. Took a measurement reading every half a second, and I collected about 60 or 70 of those readings and did an average of each one. And then I set them up here. You can see in the colored, they're measured at temperature 7, 6, all the way across. And then on the far right, you can see which test that was done on. And for each test, it corresponds to the width or the spacing between the panes. And I have the measurements of each spacing because they weren't exactly 1 to 10 centimeters. After collecting all the data, I did an analysis and calculated out all the values. Now to do this, I used 3 of the equations that were given in the book. Each one has different ranges for their Rayleigh number, the Prandtl number, and also the H over L value, which turns out to be a pretty important factor for the ratio for the size and the free convection. And as you can see on here, I've created a chart which relates the heat transfer to the spacing between the panes. And what I've been able to find was that there's a good trend that shows as you get thinner and thinner panes, spacing between the panes, you get smaller and smaller heat transfer. From what the fundamentals of heat transfer textbook tells us, we know that at a Reynolds number of less than about 1,000, the buoyancy force becomes so great that the primary method of heat transfer becomes conductive heat transfer and not free convection. And so that's kind of at the point, or that sweet spot. And something that I didn't realize in this particular experimental setup, the H/L value aren't large enough to hit that range. And so when I corresponded with the results and checked them, you can see this nice trend which supports what the book shows, although it doesn't get down low enough to that point. And so I found the trend and it matches up really well, and that it also just supports the equations and how they work, so that I can see the same trend even with the rough setup that I have. In conclusion, I had determined that for this experimental setup, I hadn't gotten out of that point where free convection was still the driving heat transfer. And so throughout all of the experiment, the heat transfer was primarily driven by the free convection circular flow that you get between the panes. And so I had done additional research, and I had found that in order to get small enough, you just have to have much significantly thinner or much taller window. And my setup wasn't set up for that. And so the additional research that I had found, I'd found a good site that they had done a similar experiment and had found for their windows, which were roughly like 4 feet tall, they found that the best spacing between there to minimize the heat transfer is 5/8 of an inch. And so that's not too big and not too small. And that gives them an H/L value of about 77. And the way that relates to my experiment is in order for me to match that same, because my H/L value is 6 exactly. And the way that I would need to match that would either to have a much taller window or to have a much thinner spacing. And I would have to be almost 1 meter tall to make that work, or to be less than 1 millimeter thin to make that work. And I wasn't able to set that up. I find this information very useful because if you ever want to create good insulation, minimize heat transfer, to have that sweet spot, you have to understand that at smaller dimensions or shorter heights, shorter windows, you need to have much thinner spacing between the windows, to the point where you might even get contact between the windows, which would really ruin everything. And so you really have to be careful about how you use that, because that